Check, check, check. Carissa, can you hear me okay?
Yes, sir, I can.
Okay, thank you. All right, almost ready to go, almost ready to go. Yeah, so like this is normally what I do for a class is something like this. We're probably yeah. This is what I normally would do. So I'd just be standing in front of the board and work out problems and record that later. What's that? No, that's actually my decent camera. That's 720 because I'm not going for high def. You need to be able to see the board, right? So I go and the lower the resolution, the smaller the file size, the quicker it is for me to upload. No, what I'm talking about is like, let me see. I have some really old ones, but I'm not even quite sure how I would find my older ones. Yeah, anyway. Technology's come a long way. I'm sure y'all have, maybe not. Have y'all heard of something called photo math before? I mean, I'd heard about it before, where you can like take your phone and take a picture of an equation and it'll solve it for you and stuff. And I was like, how good could that be? You know, like, come on. And I tried it the other day. I was like, holy shit. Like, it's amazing. It is amazing. And so technology's come a long way. I mean, that's not necessarily a good thing for a student trying to learn math and then just using a system to solve it. But, you know, depends on what you want to do. If you want to build bridges and planes and, you know, be a true engineer, you can't cheat your way through math. It'll catch up to you. But if you're trying to be a doctor and they've given you calculus 2 as the requirement, and I kind of understand that, but so when I first started teaching, if you want to be a doctor, the highest math you needed was pre-cal. And you could sometimes get away with statistics and you could go to medical school, but they had too many people wanting to be doctors. So anytime you have too many people that want to do something, they just increase the math requirement. So it's gone from pre-cal to Cal 1 to like most major universities now. If you want to be in pre-med, you got to take Cal 2. So that weeds out a bunch of students, right? That automatically just gets rid of a bunch of them. So that's not my, it's nothing to do with that. But yeah, so y'all have a good weekend. I was busy. I don't remember. I was busy doing things I like to do. So I was, I like to build stuff, wood, like wood. I like to work with wood. So I've got like a wood shop. My garage is converted to like a wood shop and stuff. So I build American flags, like American and Texas flags, like burnt. Have you ever seen those before? Burnt wood flags. It's a flag, but I'll have to show you a picture. I'll bring a picture next time so I can show you what I'm talking about. It's hard to describe, but I just do it as a hobby. And then my wife gets on Facebook and she sells tumblers, you know, those cups. She like designs cups and stuff. That's her hobby. And then she advertises my little flags. And then I don't sell them for, you know, it's not a job. It's just fun. So, but wood's gotten so expensive. It's like kind of not worth it right now for me. Anyway, but I was messing around in the garage with some stuff and I have a CNC machine. So I was reprogramming it to do some stuff. So anyway, all right. So today we are, I think I'll be able to hand the exams back next class. All right. I'm sorry that you've had to wait. But next class, you should get those back. We're going to move on. Remember last time we had started talking about exponential functions, and I had been folding the pieces of paper and showing you all that, right? We had talked about bacteria and things like that. So we are going to now officially start this section 6.3 exponential functions. All the homework for this section is here. Now, did y'all see I sent out an email with a link to a folder where I'm dumping the notes for the class now? Yes. So check that out. Check your email. Make sure you find that email, because if you click on that, it'll take you to a folder. And what you'll see is a copy of these notes. And that way, when I tell you what your homework is, you'll be able to go and open this up later, and you can just do this, right? So the first page of today's file is your homework, and it shows you what to do. Do all of these, do the odds here, and that's it. That's your homework assignment. So that'll be the first page. So exponential functions, we need to first start by reminding ourselves of the law of exponents. These are things that are learned in your first kind of exposure to algebra. These are the exponent properties. So I want to just kind of give you each of these properties, an example of each of these properties. So like for this first one, if we have a to the s times a to the t equals a to the a plus t. So something like this, if I had 3 to the 4th power times 3 to the 7th power, the property says that if you have the same base, right, they both have 3's down here, and we're multiplying, that all you have to do is add up the exponents. 4 plus 7 would give you 11, right? That's the first property in action. The second property, which I'll do this one, says that if you have something like 3 to the 4th, and then you raise that to the 7th, here you have one base to a power, and then all of that to another power, you will multiply the two exponents together. So this would be 3 raised to the 28th power, right? The next property says that if you have two things in parentheses that are being multiplied, let's say 3 times 4, and let's say I want to raise that to the 5th power, that the power can be applied to each one individually. So you can turn this into 3 to the 5th times 4 to the 5th. Of course, we could figure out what these numbers are, right? But I'm just showing you the property. Although 3 to the 28th on your calculator might cause a problem, because that's a huge number. But yeah, that's those first three. Any questions on those? You've got to be real careful with this one right here, because what if you had 3 plus 4 to the 5th? Is that the same as 3 to the 5th plus 4 to the 5th? No, this does not work this way, all right? You can only just, it's not even distribution. You can only apply the power to each of these factors if there's multiplication between them. If there's addition between them, you are not allowed to apply the power to each of those. So this is no, all right? Be careful there. All right, this next one says 1 raised to any power is 1. I think that's pretty self-explanatory, right? 1 squared, 1 cubed, 1 to any power. What about 1 to the 0? Well, yeah, because this property says any number to the 0 is 1, right? Now, there is an exception on this one. There is an exception on this one. If I take, let's say, 4 to the 0, the answer is 1. If I take 5 to the 0, the answer is 1. If I take 7 to the 0, the answer is 1. But what about 0 to the 0? Well, it seems reasonable to think that that would be 0, right? Because 0 raised to any power should be 0. But at the same time, anything raised to the 0 is supposed to be 1. So which is it? Is this 1 or is it 0, right? You can think about it. Well, it turns out this is undefined. Just like, you know how when we try and divide by 0, we're not allowed? Here, 0 to the 0 is also undefined, just like division by 0 is undefined. And so that's why in this note here, it says right there, it says A must be a positive number and B must be a positive number. They're being very clear to make sure you don't accidentally try and plug 0 in right here, because then this property would not work. And then this middle property says that if you have anything raised to a negative number, it's the same as 1 over that to a positive number. So I'm going to show you that one in an example. So let's say we take 4 to the negative 2. According to the property, that's 1 over 4 squared. And then we could go even further and write that as 1/4 squared. Because if you take a fraction, you can square the top and bottom. When you square 1, you get 1. And when you square 4, you get 4 squared. So this is really just kind of peeling that power of 2 outside and looking as a fraction 1 over the 4 to the second power. All right, any questions on those? Those are going to come up kind of sporadically through the next couple of sections. Make sure you're bringing your calculators from here on out, or you have them at the ready. Let me see if I have mine. I actually think I may have forgotten mine. Yeah, we will need our calculators to calculate some things now. So please bring those. I'll let you use your phone today if you need to. I might have to use mine. All right, that's it. So we're ready. Let's get into exponential functions. And we did talk about this last time, but now we're going to formally explain what an exponential function is. So in general, an exponential function, now I added something the book didn't put here. An exponential function of base A is a function of this form. F of x equals some constant c times a to the x. So when you look at this, I want you to look at that as being some constant, some number times a to the x. Now it's important that you understand that according to order of operations, you must always do this a to the x. You must figure out what this is before you ever multiply by this c. You can never multiply the c and the a together, right? Order of operations says parentheses, exponents, multiplication, division from left to right, addition, subtraction, left to right. So you'd always have to do this exponent first before you do the multiplication. So don't ever multiply these two numbers together. Fair warning, right? So all exponential functions look like this. And what we said last time is that the thing that makes an exponential function exponential is the fact that the variable x is up in the exponent as opposed to down on the bottom. You know, we have studied already things like f of x equals x squared. That's what we studied before. This is a polynomial. It's actually a quadratic. That's not what we're looking at. We're looking at things that look like this. F of x equals 2 to the x. Here, the number is in the bottom, the base, and the variable is up in the exponent. So, for example, for this one right here, what would a be for us here? 2. And what would c be? 1. Right? Do y'all see that you could really write this as a 1 times 2 to the x, right? So this is your c, then your a to the x, so the 2 is the a, right? Any questions? Now we have some conditions on a. A can't be just any number you want. To be an exponential function, a, first of all, has to be a positive real number. Okay, so that a that we put in there has to be a positive real number, which means it has to be greater than 0. The other condition we have is that a cannot be 1. Now, the reason we say a can't be 1 is because 1 raised to any power would just be 1. So this would be a very boring function because all it would be doing is just being the same thing the whole time. It would just be a flat horizontal line. So we remove that. And then we also say c can't be 0. And the reason we say c can't be 0 is because if c is 0, then it kills everything off. And we don't even have, well, then the a to the x doesn't matter anymore. It's just 0. So it's a very boring constant function. So as long as we have a is positive, a is not 1, and c is not 0, then we have an exponential function. Now, the a that we have here, whatever that number is, like here it was 2, whatever that is called the growth factor, okay? And the c that we have in front is called the initial value. Now, when you hear initial value, the word initial means like starting value. The starting value of the function. And the way to understand why c is called the starting value of the number is that if you take this function And you replace, so let me write it down here. If I take any exponential function that looks like this, if I were to try and figure out what happens when you plug 0 in, 0 would be like where you start, right? X is 0 would be the initial value. If we try to plug 0 in, then we're going to get c times a to the 0. But we already said a to the 0 is what? 1, right? So this is just c times 1, which is c. So for all exponential functions, right? For all exponential functions written like this, then c should be the value we have at the very beginning. All right. Now, before we start looking at the graphs of these, which is really what the next part of today is going to be, we want to be able to identify the difference between a linear function and an exponential function. So what we're going to do is look at these tables. This is like a t-table, good old-fashioned t-table, where you plug in x, spits out y, plug in x, spits out y. And these are for 3 different functions. I'll call it f, g, and h, okay? 3 different functions. And it's asking us which of these are linear and which of these are exponential and which is neither linear nor exponential. So let's start with the first one. Notice that on the x values, they keep going up by 1 each time, right? 1, 1, 1. So you start at -1, then 0, then 1, then 2, then 3, right? So as we jump from here to here, it just goes up +1 here, +1, +1, +1, right? The whole way. But what do the y values jump by? -3, right? It goes down 3, and then it goes down 3, then it goes down 3, so subtract 3. So do you all see that there is a constant rate of change of the y value? It's always the same. The x values go up by the same amount, the y values go down by the same amount. Agreed? Is that what's happening on the next one? Let's see. This goes up by 1, 1, 1, right? So these are all going up by 1, add 1, add 1, add 1. But what about these? To go from here to here, you could say subtract 16, right? Let me try that. I'm going to put it down here. I subtract 16 to get from here to here. But what about here to here? Now I'm subtracting 8. And what about here to here? Now I'm subtracting 4, and then here to here, I'm subtracting 2, right? That's not the same as what's happening here, right? Here they have a constant rate of change. Here, it is not constant rate, right? In order for it to be constant, it would have been -16, -16, -16, -16, right? But how about this? Instead of that, why don't you think about it as not what's being added or subtracted to get from one line to the next, but what's being multiplied or divided. So to get from 32 to 16, don't I have to half the 32? So instead of saying this, let's look at it as I am multiplying by a half to get from there to there. You could say divide by 2. Yep, I'm going to say multiply by half. Divide by 2 is the same thing. And then what about 16 to 8? Half again, right? Take half of 16, you get 8. And then you go again, half. And then half again. And we keep going, right? Here, this was subtraction. We have the same subtraction each time. Here we have the same like multiplication, the same scaling of the numbers as we move. This is the difference between exponential and linear. What you're looking at here is linear, because this is a constant, either adding or subtracting from each one. And then this one is exponential, because this is a constant multiplication or division as you go from one to the other. Do you see that, the difference between the two? Now, what about this one? These keep jumping by 1. Okay, how about from 2 to 4? Let's look at it with an addition or subtraction first. What would it be adding or subtracting? It would be adding 2, okay. Then here to here, adding 3, and then here to here, 4, and then adding here to here, 5. Okay, this can't be linear then. Because to be linear, we would have to have this be a constant rate of change, right? Constant. This would have to be 2, 2, 2, 2, or 3, 3, 3, 3, or something like that. So it's not that. How about, is it a constant? Oop, I forgot a T there. Is it a constant multiplication or division? So how would you get from 2 to 4? You would have to do what? You'd have to multiply by 2, right? Now that gets you from 2 to 4, but now that pattern needs to hold. And it doesn't, does it? Because if to continue this pattern, I'd have to have 4 times 2. This would need to be 8, wouldn't it? And then the next one would have to be 8 times 2 is 16. Next one would have to be 32. So this is not going to hold, right? Nope. So it's neither. You don't have to be one or the other when it comes to functions. It can, but you need to understand the difference between linear and exponential, because I think it's easy to identify, I think, if you just look at it, do they have the same sum or difference between the y values? Do they have the same factor or multiplication or division from value to value? All right, so neither here. Next thing. What do exponential functions look like? What do the graphs of these look like? So what I'm going to do here to start is I'm not going to look at this. Now remember, when we started this just now, right? We said all exponential functions look like c times a to the x, right? C times a to the x. I want us to right now just act like c is 1. Okay, so if c is 1, if this is 1, then this just becomes a to the x, right? And what we're going to look at is, what does a to the x look like if you graph it? All right. And here's the graph. So hopefully, yeah, I think you can see this okay. Right here, I've made this little thing where I can control what a is. So right now, what we are looking at is the graph. This graph right here is the graph of f of x equals 2 raised to the x. Okay, do y'all see the 2 right over there? Okay, so right here is what the a is. So let's talk about what this graph looks like. And I'm gonna zoom out a little bit. Whoa, that is weird. That's not supposed to do that. That's the computer freaking out. That's not supposed to look like that. I'm gonna go like this. Okay, there we go. So what does it look like happening here? What would you say the domain of this function looks like? 0, domain or range? Negative infinity to infinity. So if we look at the graph, to the left, the graph keeps going, right? And to the right, the graph continues. It goes way up, but if I keep moving to the right, it keeps going up. So the domain looks like everything, all real numbers. What about the range? 0 to infinity. Do we ever actually take on the value of 0 though? Does it look like we ever get to 0 there? Or are we just getting there like asymptotically approaching it? Like remember our rational functions? When they would go towards that magnet and never get there? Does this look like what's happening here? It is, okay? That's exactly what's happening. It's getting closer to the x-axis. It's never getting there, okay? So the range of this would be from 0 to infinity, not including 0. Now, I will summarize all this in a minute. Just trying to get us to look at it all. So domain's everything. Range is from 0 to infinity. Is this function increasing or decreasing? Increasing, right? As you move from left to right, you're constantly going up. Do we have any x-intercepts? No x-intercepts, right? Because we already said it never hits the x-axis, right? We have no x-intercepts. What about y-intercepts? We have 1. Where is it? The y value is 1, right? The y value is 1? Yeah. Okay, so we have one y-intercept. It's increasing. We got domain and range. All right, let me change this. Let me change that to a 3 instead of a 2. Let's see what happens to the graph. You ready? There, now I'm at 3. Not much changed, huh? What would you say? It got a little bit steeper? Let me do that again. Here was 2. Here's 3. And if I go 4 or 5, it's just getting steeper, right? Did anything happen to the y-intercept here? Did that change? Let me move it back and forth again. Did the y-intercept change? No, the y-intercept stayed the same, right? Did it change the fact that we have a horizontal asymptote? Nope. Did it change the fact that it takes off real fast? No. Just change how fast, right? So for all exponential functions, it looks like they have this same sort of characteristic, right? The same behavior. Well, hold on. We tried 2 and 3. What about some numbers that are smaller than 2? Let me go to like 1 point something. But we're still doing the same thing, right? Still doing the same thing. Okay, until it's starting to flatten out a little bit, isn't it? 1.1. Okay, okay. See, if I zoom out, it's still doing the same thing, right? All right. What about if I do 1? Well, wait a minute. Didn't we say you can't have 1? That's exactly why. Because once you put 1 in there, it's no longer going to do this thing. Okay, so I'm kind of tricking you here. You're not supposed to do 1. Let's do something smaller than 1. Hold on, I need to change this. I need to stop this at 0. Okay. Okay, so here we go. We're at 1. Oh, okay, so here was bigger than 1. Let me zoom out a little bit. Here was bigger than 1. And then watch, I go, and when I go to something that's smaller than 1, 0.9 something, look what happened. Look at that. Remember, A has to be positive, doesn't it? A can't be negative. So I'm putting in numbers that are bigger than 0, but they're smaller than 1. And isn't it almost like it's flipped over? It's like a reflection over the y-axis, isn't it? It's like, here's A bigger, these are A's bigger than 1, and these are A's less than 1. Bigger than 1, less than 1, right? Does that change the y-intercept? No, still stays the same. Is it have the same domain? Yeah, graph goes to left and right forever. Does it have the same range? Yeah, is it increasing or decreasing? Decreasing this time, right? Same y-intercept though, okay? So these are like the 2 scenarios we can have. And this is where I'm gonna go back to the notes and kind of look at this. When it comes to exponential functions, we have one of 2 things, the one on the left and the one on the right. The one on the left is called exponential growth. And that will always happen when A is bigger than 1. It will look like this. It will go through the point 0, 1, that's your y-intercept. Out the left side, it will have a horizontal asymptote of the x-axis. And then pay a close attention to this detail right here. What I just highlighted in yellow. What I'm saying here is that for this function, as x goes to infinity, the function goes to infinity. So the arrow means, look, imagine what would happen if x gets really big. Okay, so x is right here, right? If I start going out to the right really far, really far, really far, what is the function doing? Well, it's taking off, right? Where is it headed? Off the page, right? Way up to infinity. Do y'all understand what this in yellow is saying? As x goes to the right forever, the function goes up forever. Does that notation make sense? That's the way we look at things in calculus. We use these little arrows to infinity and stuff like that to get a feel for what's happening with a function. It's increasing, right? From right to left, you're always going up. Okay, so all of those things are summarized right here. This is out of the textbook. I'm not going to read through it. It talks about domain, range, y-intercept, what's happening as you move to the right. I didn't put it here, but what happens, you know what? I should have put it here. I don't know why I didn't. What happens if we look out the left side as x goes to negative infinity? So as we start looking at this graph out the left side and keep going to the left, head towards negative infinity, what does the function head towards? 0. Does that make sense? As we head out to the left, okay, here we go. What's happening to the value of the function? It's getting smaller and smaller and smaller. It's headed towards 0. Make sense, Amanda? If we were walking along this function and we started to head to negative infinity, that means we're going to start walking out to the left. As we walk, how high off the ground we are is going to get smaller and smaller and smaller. We're actually headed to 0. Whereas here, headed to infinity means we're walking along to the right and we keep getting higher and higher and higher, right? Okay. So that's exponential growth. That will always happen if A is bigger than 1. Okay, so if A is 2, it's going to look something like that. If A is 3, it's going to look something like that. If A is 10, it'll look something like that. Now, if the base of the exponential is between 0 and 1, then it's going to flip over and look the other way. Okay, it's going to look like this. And in that case, let's see, it's decreasing. We have the same y-intercept. Our horizontal asymptote is on the right-hand side, though, this time, instead of the left. And as x goes to negative infinity, that means, Amanda, we're standing here, we're walking to the left, our function is going to force us to go up, right? So as we walk to the left, the function wants to go up. What about if we walk to the right? What if we say, hey, let x go to positive infinity? So start walking along the right, out the right side. What's happening to your function's value? It's going to 0. So as we go out to the right, the function dives off and gets smaller and smaller and smaller. All right. Exponential functions are real important. I mean, I gave you some examples in bacteria, the COVID, right? The whole thing that's happened with COVID over the last year and a half, 2 years, right? Started out just a few people and then it just blows up, right? That's the way viruses grow. They grow exponentially. And if you ever watch the news, I don't know, the news is where I hear this word the most, exponential. They say, oh, you know, crime is growing exponentially. And they usually misuse the word. They usually misuse it because exponential growth is a certain type of growth and crime doesn't grow exponentially. I mean, it's not like, you know, you have one homicide and that causes 4 homicides and each of those causes 4. They just like to throw that word out there because it makes people think, oh, it's really growing, you know, but technically it's a certain type of growth, right? All right, questions on this? You just need to know the basic shape of a graph. So now what we're going to do is we're going to get our calculators out and we're going to actually graph these two by hand. So if you have your calculators, here's what we're going to do. For part A, we're going to sketch this. Our function is f of x equals 1.75 to the x. Now, just tell me right off the bat, is this exponential growth or decay? Growth, right? Because the base is 1.75. So we should expect, when we do this graph, this is not our graph, but what we should expect to see is something that looks like this. Right? That's what we should expect to see because it's exponential growth. Now, to do it, here's what I want everyone to do. That way, all of our graphs look the same. We're going to do this using a t-table. Now, you know, coming into this, y'all just took a test, and you know from the beginning of this class, graphing a line was easy, right? Like relatively speaking, graphing a line is easy. A parabola, a little harder. There were some steps. Polynomials, even harder. And rational functions were just a pain. Exponential functions are the easiest to graph out of all of them because all we're going to do is a t-table and use our calculators because we already know the basic shape of the graph. It's not going to deviate from that. So I just need to kind of get a couple of points. That's it. So I want everyone using the same points. Here's our x. And this is going to be 1.75 to the x. And everyone is going to use these 7 points: -3, -2, -1, 0, 1, 2, and 3. And that way, if we all use those same numbers, we will all get the same basic picture. So on your calculators, you need to be able to do 1.75 raised to -3, and you're going to get a decimal answer. 1.75 raised to -2, 1.75 raised to -1, and so on and so forth. 1.75 raised to the 0. I already know what that one is. That's 1, because anything to the 0 is 1. That's that y-intercept. A y-intercept's always going to be there, right? And then we have, let's see, 1.75 to the first power. That's 1. 1.75 squared, need a calculator. 1.75 cubed, need a calculator. All right, I'm going to need some help here. Somebody get 1.75 to -3? 0.19, okay? And let's just round like 2 or 3 decimal places. You don't have to go much on that. Next one? 0.32, thank you. Next one? 0.57. And then we have 1, and then 1.75, forgot to put that. How about squared? 3.06. And finally, good. So make sure, does anyone disagree? I want to make sure people are getting these answers, because this, you know, this will depend on your calculator. If you need help figuring out your key, now would be a good time. You know what keys to push?
Yes, sir.
Okay.
On the -2, I got 0.326.
Okay, that's fine. You could round to 0.33. You'll see what I'm about to do. See, we're going to graph this, right? We're going to graph this. So we're going to plot these points. Nobody in here is going to be accurate enough down to the nearest like 100th of anything, because it's just impossible to graph that accurately. So it's okay if you round it up or down. Just don't round 0.3 to 0. Like, don't round it all the way down to 0. And, you know, don't round 1.75 up to 2. 100th is fine. I don't care how far. Yeah, the second decimal place is good enough. So now we're going to graph this, right? So the way I'm going to think about this when I go to graph it is, okay, well, it's an exponential function. It's exponential growth, right? So I know I'm really only going to have graph up here, right? Because all exponential functions, the graph is above 0. So I'm going to put that like this. I know my x values go from -3 to +3. So I'm just going to put like three tick marks each direction here on the x. And then as far as the y value, this is probably the most important part of this, is to figure out what's the smallest and largest y value we have. Well, 0.19, it's really close to 0, right? That's like close to the x-axis. And then 5.36 is the biggest number we get, which means on my y scale, I want to go up to 5, okay? And so if you were doing another problem, let's say that this number was 50.36, 50.36. I would need to make sure my scale went all the way up to 50. So maybe I count by tens or something. But because it only goes up to 5, here's the way I'm going to do it. I'm going to count like this. I'm going to say that's 1, 2, 3, 4, 5, and I won't even need to go higher, much higher than that. So now I'm going to plug in my points. So I'm going to start with the middle one, because that's my y-intercept. When I plug in 0, I get 1. I'm going to do that in red. That point lives on my graph. When I plug in 1, I get 1.75. So I go out 1. I go up about 1 3/4. We are, that's 1.5. We are kind of eyeballing this. You just don't want to be way off. At 2, we're at 3.06, so a little bit above 3. And then at 3, we're up at 5.36, so somewhere up here, like that. Those 3, or those 4 points. Now, the other points are little decimals, right? 0.57, 0.32, 0.1. I can try and like squeeze those in there, can't I? But I know something about this. This is exponential growth. So I know I have a horizontal asymptote coming out the left side, right? I know that. So when I draw this, I'm just going to draw this like this. I'm going to make it dive down. And I'm just going to make it get closer and closer to the x-axis, draw an arrow. And then up the right side, I'm just going to draw an arrow and I'm done. Okay, it doesn't have to be perfect. It's just to give us a basic idea of the graph. Aren't you happy? I mean, this is way better than rational functions. Yes, way better. There's nothing, no factoring involved. There's no, horizontal asymptote test case 1, 2, and 3, right? Nope. Just is it growth or decay? Plot some points. You're done. I'll leave the next one to you to do on your own. 0.6 to the x. That will be what type of do we have? What type do we have there? Do we have growth or decay? That's decay, because 0.6 is smaller than 1. Not right now. You don't have to do it right now. I'm just saying do that on your own and draw it out. Maybe at the end of class, if you want, we can practice. All right. You ready to move on? All right. So now we're going to talk about a very special base. So as of right now, we have this general idea of an exponential function looking like this, right? That's our general exponential function. And this base, that a, right? The a is called the base. That can be any positive number except 1, right? Any positive number except 1. So we've seen 2 in there. We've seen 1.75. We've seen some other numbers, but any positive number. So I want to start by talking about a number you all know, which is the number pi. Y'all are familiar with the number pi. You see that when you're looking at areas of circles, right? There's a formula for the area of a circle. It's area equals pi r squared, right? But there's also a formula for the circumference of a circle, which is circumference equals pi times diameter. So pi comes up whenever we're dealing with circles. What I want you to understand about pi is this. It's an irrational, not number, it's an irrational number. We call it an irrational number. All right. And what makes a number irrational isn't that they don't listen, they do whatever they want to do. And that's an irrational person. Okay, an irrational number means that it's not a ratio, means it's not a fraction. Okay, so a lot of people think that every number out there can be represented as a fraction. And it turns out that that's not the case. If you were to look at, all the numbers on the number line and just go pick me one, okay, the chances that that number right there, if you just grab it randomly, the chances that that number is actually a fraction is essentially 0. There's like almost no chance. There's so many numbers in there that are not fractions, and all those numbers are called irrational. And pi is one example. Now, what makes a number irrational is that when you look at it, it is a non-repeating, non-terminating decimal. So I'm guessing all of y'all have heard that pi is approximately 3.1415, but this keeps going forever and doesn't have a pattern to it. Have y'all heard that before about pi? Yeah, that's what an irrational number does. There's no pattern to it. It's just like each number that comes next is just something that doesn't in any way come from anything before it or after it. It's just almost seems random. Nobody has been able to find a pattern in pi. There is no pattern. All right. The world, I think the world record for the number of digits that somebody has memorized pi, 19 digits? Oh no, the world record? No, 19, no. My colleague that I work with has it out to 120. But that's because he was born in the 40s and back before calculators and computers, people had to know pi because you didn't have a calculator to go to. You had to know pi in your head, and you had to know other numbers in your head. So it used to be back before calculators and computers that it was kind of like a something to show off. Like if you were really strong in math, it would be like, well, how many digits do you know pi? And seriously, I'm not kidding. And it used to be like, well, I know it out 60. How about you? 80, you know, and seriously, they used to like have competitions and stuff. And so I honestly, for me, I don't know pi past like 5 or 6 digits because I don't care, because I have a calculator and I don't need any part of my brain to have to memorize anything, right? It's like, it's there. So different times, different age, you know, different day, different age, right? The world record, though, I believe is 60,000. It could be wrong, could be 16,000, but it doesn't matter. 16 or 60,000 is still a lot.
It's like
And
68,000.
what is it?
68,000.
Did you look it up already, or did you just know that?
No, I knew that from calculus from high school.
Oh, really? They told you that? 68,000? Yeah, so it's really actually interesting. The person who has the world record, the only reason that he stopped wasn't because he got that last digit wrong. He was just tired. He was just like, he had been, you know, reciting the numbers like for hours and hours and hours and hours and hours. It's really interesting that they interviewed this person, and you know, the way that he thinks about numbers is very different than the way a lot of us think about numbers. So like, if I asked you to memorize 50 things right now, right? 50 things, that would be really hard for you to do. But if I asked you to describe 50 things that you would see if you got out of your bed and walked to your garage, could you list out 50 things? Do you think you could? Like, you get up, you could probably say, oh yeah, there's a table there, right? I have that picture on the wall. I have this, that, walk through the kitchen. I got a stool there. You're right. Like you could do that. You could, I'm sure, come up with 50 things describing that. That's the way that this person sees numbers. It's more of like a scenery. It's more of like he you know, goes 3.1415, and he's actually just seeing the scenery go by him. And it's very easy for him to just recall that. So really weird. I mean, the human brain is very interesting, obviously. Okay, that he didn't get any awards or anything, you know, just like, good job, pat on the back, you got the world record. But I mean, we have computers that can take pi out to trillions of decimal places, trillions. So, you know, and it really, in the real world, when it comes down to, if you're building a bridge or an airplane, you only need pi out so many digits. You don't have to go that far, because, you know, there's theory, right? There's the theoretical pi. Like, if you ever stop anywhere in pi and stop, you have now rounded. There's now error. That's not really what pi is. But in the real world, when you're manufacturing something, you can only manufacture within a certain precision anyway. So there's going to be error anyway. Like, does anyone think that a soda can holds exactly 12 ounces of soda in it? No, it's 12 plus or minus, right? We can only go so precise on anything. So it's okay. This is something my Cal 2 students really, when they realize that, like, you don't have to have exact answers in the real world. You just have to get close enough to be within a certain tolerance, then all these approximations are okay. You just have to be careful. You have to be careful, because there's times you can get in trouble for that. All right, we move on. So pi is a number I think most of us are familiar with. It's just one of infinitely many irrational numbers. It's so special to us that we give it a Greek letter, right? Pi is a Greek letter, so it's special, right? Well, there's another special letter called E. Y'all heard of that before? It's just like pi. It's an irrational number, but it's so special, we give it a letter. We give it the letter E. And that letter E comes from the mathematician who pretty much came up with the idea of E, and that's Leonhard Euler. It looks like Euler, but it's really pronounced Euler. And he lived in the 1700s. Brilliant mathematician. I have a book in my office that has it's called the Precise Encyclopedia of Mathematics. My brother gave it to me when I graduated from graduate school. It's this big encyclopedia of math. And if you look up Euler in there, he has 30 pages of that book. I mean, the book's huge, but 30 pages for one person is pretty amazing. So he has lots of contributions to mathematics. E is this number, right? It's irrational. It's approximately 2.718. Pi is about 3.1415, but this E is about 2.718, and it goes on forever. There's no pattern to it. But the thing that's weird about E is the definition of E. Like pi has a very simple definition. Pi is always just the circumference of a circle divided by its diameter. That ratio is what pi is. So people can like put their heads around that. Okay, if I had a circle, if I were able to cut it and undo it and lay it out, okay, that length would be the circumference. Take that number and divide it by the diameter, and that's what pi is. Like that seems like something very physical in front of you that you could actually like manipulate if you had string and stuff like that. The definition of E is crazy. It's well, not crazy, but it's weird. Okay, so here's where it comes from. E is the number you get when you take this expression, 1 plus 1 over n, all of that raised to the n, and you start letting n get infinitely big. So let me ask you right now, if I plug 1 into this, what would you get? If I ask you to plug in 1. So 1 over 1 would be 1, right? And 1 plus 1 would be 2, and 2 to the 1 would be 2, right? 2 to the first power. So if you plug in 1, you get 2, yes? Now, if I have you plug in 2, you'll get 1/2 plus 1. Half plus 1 is 1.5. And if you take that and you square it, now see, because now I plugged in 2, right? Square it, I would get 2.25. Now, if I plug in 3, I get another number, 4, another number. In this table, I already did it for you, shows what happens when you plug in 1, 2, 3, 4, 5. And notice what's happening in this table. It starts out at 2, 2.25, and you keep going and going and going and going and going. And then I'll continue up here, and look at these numbers. They're getting closer and closer, 2.6. I haven't even made it. I've gone 60. I've plugged in 60, and I'm not even at 2.7, right? So let me show you the graph of this, like what it would look like if we graph this. I have to hide this. Where is that? Where'd it go? Oh, it's a different one. Hold on. There we go. Okay, so here we go. Hope you can see this. I have the computer doing this for me. Remember what we just said? When you plugged in 1, you got 2, right? And then when we plugged in 2, we got 2.25. So when I plug in, oh, shit. I don't know if I'll be able to do it. Hold on. It's too big. Do that. All right, so when I plug in 1, I get 2. When I plug in 2, I get 2.25. 3, I get 2.375. And then now I need to let it get real big. So let me change that. So now watch what happens. $2.7. Do you see that the graph of this thing looks like it's getting closer and closer to something? Well, that number is exactly what E is. I had the computer plot E for me, which is 2.718 something. So the further out you go, the closer and closer you get. But this is like a horizontal asymptote, everyone. It's getting closer and closer, right? That is a weird way to define a number, isn't it? To say it's basically what happens to that graph if you go out forever. But that's the definition of E. All right? Weird stuff. Now, what makes E so special? I mean, at the end of the day, it's just a number, right? At the end of the day, E is just a number. And it's bigger than 1, isn't it? About 2.718. So if I graph it, it should be exponential growth, shouldn't it? The graph of this should be exponential growth because that number E is bigger than 1. So it should look like this. But what makes it so special? Why is it so special? Well, unfortunately, to explain what's special about it, really you have to understand some calculus, which you haven't taken, but I'm going to give it a shot. I'm going to give it just a real small shot here. So to kind of motivate this, I want to go and have you look at something. Here we go. I want you to look at the graph here of x squared. Okay, this is the graph of x squared. And what I've done here is I've drawn on this graph of x squared this thing we call a tangent line. It's a line that hits the graph at one point and runs tangent to the graph. So it's just barely kind of balancing on the graph on that one point. Does that make sense? As I move this point around, as I move that point around, right, that tangent, that dotted line changes, doesn't it? And since it's a line, it has a slope. What would you say the slope of that tangent line is right there? What's the slope? If it's horizontal, 0. The slope should be 0. Rise over run. What if I move it just a little bit to the right? Let's say right there. What would you say the slope of that is? Well, this is x squared. This 0.25 is actually, this 0.5 is how far out and over the, to the right and how far up that point is on the graph. Right now, I have the computer. Where is it? I have the computer it's going to calculate the slope for us. Okay. The slope of this blue line is 1. Y'all see that? You just have to believe it. Does it look like the slope is 1? Go up 1 over 1, up 1 over 1. Does that look about right? Looks like a diagonal to me, right? So at this point, the point on the graph is 0.5, 0.25, all right? But the slope of the line there is 1, all right? And now as I move to the right, now look at there. The point that we're at is 1, 1, right? Go to the right 1, up 1. What's the slope of the line here? According to this, it's 2, right? All right. And let's move out a little bit more. Let's go to here. Oh, whoa. Right there. So here we go to the right 2, up 4, and there's the point, right? What's the slope of the line here according to the computer? 4. Hey, wait a minute, hold on. This 4 matches this 4, doesn't it? That's kind of a coincidence. That's the first time it's happened, right? Do y'all see that the y coordinate on the graph? Okay, so how high up the point is 4, right? This point is 4 units high, matches the slope of the line. Doesn't it? It matches. Now, if I back it up a little bit and go back to here at 1, how high up is that point? 1, but what's the slope? 2, it doesn't match, right? I wonder, and this is what mathematicians and human beings were trying to figure out, is there a function that does this? You know where they matched? Right there, they matched, right? The height of the point was equal to the slope. Mathematicians and physicists and chemists were all like, I wonder if there's a function that this happens at every point. So at every point you go to, the height is equal to the slope of that tangent line. And we didn't know if there was a function that actually did that. And then we discovered, yes, it does happen, but there's only one function that happens for, and it's e to the x. It is the fundamental property that makes the e to the x so special. So if I go and I graph e to the x now, let me graph this. Let me bring that point back. So I have the computer, where is it? Hold on. I need to change this to, I need to add it, I never added it. E raised to the m. There, I'm going to have the computer calculate the slope for me. So look at this point right here. How high up is the point? 1, and then what is the computer doing the slope for? It's 1 also, right? I think that makes sense. Up 1 over 1, up 1 over 1. But if I go to the right a little bit, you go to the next point right there. Okay, so how high up is this point? 1.649. And guess what? The slope is being calculated to be the same thing. And that happens for every single point on the graph. No matter where you are, the slope of the tangent line is equal to the y value of the function itself. And in calculus, we call this slope of the tangent line, we call it the derivative. It's called the derivative of the function. And so you learn in calculus that e to the x is the only function that is the derivative of itself. So we are a little, we can't really push too hard on this because we don't know much calculus at this point. But I'm just trying to get you to understand that what makes this e to the x so special, right, is a calculus concept, and that it is the only function with this property, the only one. And that is why we call e the natural base. It's kind of like, it's just naturally occurring. We can't explain why this number is this way. It just is, okay? And it's the only one that is. It could have been a different number, but this is the one. So we call it the natural exponential base. All right, so now what I'd like to do, that was just to kind of give you some sort of appreciation for what it is. I want us to go back a few sections ago when we were learning about transformations. Remember how we learned how when you know the graph of something, then if you add a number here, it might move it up or down, or if you add it here, it might move it left or right, or if you put a negative here, it might flip it over the x-axis or y-axis, things like that. I want us to look at the graphs of these functions. I want us to sketch each one of them and talk about the domain and range. So I'm going to start with this first one. And when I say sketch, everyone, I mean like a rough sketch. Why is this not? There we go. I mean a rough sketch. All right, so what I'm going to do here to do this sketch is this. I'm going to start off, let me get grid here. Y'all doing okay? Exponential functions are a little, oh no. There's something about exponential functions that makes students just want to like turn all the volume down and just, I don't know what it is, just. Okay, so here's what I know. Basically, this is what e to the x looks like, right? That's because it's exponential growth. I don't care about all the little fine details. I just know that that's what it looks like. So what I now realize by looking at this is that the first thing I'm going to see here is that e to the x, I have a negative in front, which does what? Flips it over the x-axis. So everything that used to be positive now gets flipped over, gets mirrored over. So now it's going to look like this. That y-intercept comes down here. So now it's going to look like that instead. So this is negative e to the x, right? Does it have the same horizontal asymptote right now? Yes, it still flattens out over here. But there's one more thing I need to do. What? Move the whole thing up one, right? So think about this. What used to be your horizontal asymptote, right? Your horizontal asymptote used to come out here like this. That's terrible. Okay, horizontal asymptote used to come out here like this. Now the whole graph goes up one, which means that horizontal asymptote goes up one. So it's going to come up to here. I have to bring it all up all the way up there because this is one right there. This is negative one right here. So that whole horizontal asymptote goes up one. Every point goes up one. So I'm going to move this point up here. It's going to actually go through right here now. It'll flatten out towards that. And it'll still dive down like this. We don't have to be too particular about this right here. That blue one is negative e to the x plus 1. Understand? What's the domain? Domain is still negative infinity to infinity. What's the range? Negative infinity to 1. Include 1 or not? Do we ever reach it? We never reach it, right? So you see how The domain, nothing changed. You still go to the left forever and to the right forever. What changes is the range. The graph goes down forever. So negative infinity all the way up to 1. It never quite reaches 1. We good? Questions? We're all right? Yes. Yes. Every exponential function that looks like a to the x. So if I have e to the x, it's going to go through there. If this is 2 to the x, it's going to go through there. If this is 1/2 to the x, it's going to go through there. Now, if you start making other changes, like if you put 4e to the x, that will change things. The c definitely changes the y-intercept. Yep. Which I think we'll be able to see on the next, on one of these next examples. Yeah, like on D, when we get to D, we'll see how that changes. All right, so, all right, what about this one? Maybe I can squeeze this one in here. If we go to graph this one, I actually think this one looked pretty good. I'm gonna copy this one because I liked my original e to the x on that one. All right, what I'm going to do here is just erase all the stuff that I added later. Okay, that's basically my e to the x, right? And I'm trying to do e to the negative x plus 1. So what do? What does this e to the negative x look like? Flipped over the y-axis. So if you have a negative on the x, it's a reflection over the y. If you had a negative out front, which was the previous problem, we did it over the x. So let's flip this over the y-axis. If we flip it over the y-axis, it's going to look like this, and then go this way like that. That's e to the negative x. And then plus 1. Which moves that whole graph up 1. So now this horizontal out that's now out the right side goes up 1. This y-intercept that used to be here at 1 now goes up to 2. The graph will still go up to the left, and it'll still flatten out towards that horizontal. Oops. Towards that horizontal. So that's e to the negative x plus 1. Understand? Questions, or can I move on? I think I'm gonna need a new page for this. Okay. Tell me what's gonna happen here. Flips over the y and then over the x and then the whole thing up 1. So it's a double reflection. Let me see if I can do this one quickly. So here's my original e to the x. I flip it over the y-axis. That's e to the negative x. I flip that over the x-axis. So when I flip that over the x-axis, it looks like this. Flattening out towards that. Understand? This green one gets reflected over the y, becomes the red. Then that whole y gets reflected over the x-axis. That becomes this. And then the whole thing just moves up 1. So when I move that up 1, this comes up here. This comes right here. And we get this thing. I didn't do domain and range on the last one, but I think y'all understand it now. Yeah. Let's look at D. Maybe we can just talk through D. I don't know. What does the -3 do? Moves it to the right 3. Let's do this one. Yeah, let's do it. I think it's worth our time. I'll do it on this. Yeah, we'll take our time on this one because this one's probably the most important one. So I'm going to start out with my original graph. I'm going to be somewhat precise on this. Oh, somewhat precise on this. Let's say that this is 1 and this is 1. That way we know how we're measuring things here. So I know the original function e to the x goes through here, goes up, comes down, flattens out over here. E to the x. All right, now I need to take that graph and I need to move the whole thing to the right 3, right? To the right 3. That means every point moves to the right 3. Well, I really only have one point that I know for sure. I'm going to move it to the right 3. 1, 2, 3. That is my new, like this y-intercept moved over, right? So the graph is still going to grow to the right. And it's still going to flatten out towards the x-axis like this. Okay, that's e to the x minus 3. Now what do I look at? The 2, okay? So what does 2 do? Stretches everything out by 2, right? A factor of 2. So this point, remember how high was it? How high was this point? It was 1. Now I multiply it by 2, it becomes 2 high. It goes up 2 times 2, not add 2. Multiply times 2. So now that point goes here. That's 2. And then it still grows, but it's a steeper growth because I'm multiplying by 2. This still, oh, no, I need a little bit smoother looking at. This still drops down towards 0. And then the last thing is what? Down 4. Oh, this is e to the negative, e to the x minus 3, and then 2 in front. And now I move the whole thing down 4. So I'm going to grab that point. I'm going to move it down 1, 2, 3, 4. It's now here, right? That's where that point is. Where did my horizontal asymptote go? It's -1, -2. It was here at 0, right? Doesn't that go down? 1, 2, 3, 4. This is my new horizontal asymptote down here, like this. That horizontal asymptote drops to here. My graph is going to go up like this, and then it'll flatten out towards that horizontal asymptote like that. So 2e to the x minus 3 minus 4. What's the domain of that? Everything, right? All real numbers. And the range, -4 to infinity. Good. Not including -4, right? So domain, -infinity to infinity. Range, -4 to infinity. Okay. Doing it right? We're almost, well, we're done with this part. We're going to do more exponential stuff. We're going to shift gears slightly here now. One of the most important applications of exponential functions is solving equations. All right, so we need to see what can we actually do in terms of solving equations that involve exponentials at this point. So just first thing we need to know is that if you ever have some number raised to a power equals the same number raised to a different power, then you can automatically assume that those two powers have to be the same. This is a fundamental property of exponents, of exponentials.
X will equal y, like it'll be the same number.
That's right. These will be the same.
So if x is 3, then y is 3.
That's right. Let me try and explain what's important about this. If I tell you right now that 3 squared equals 3 to the x, then from that you can tell me that x must be what? 2. Okay. Now that may seem obvious, but it hasn't always worked this way. If I wrote this down right now, x squared equals y squared. Does that mean that double arrow like that implies Does that imply question mark that x equals y? No, why? Can you give me an example where the top would be true, but the bottom wouldn't be? Yeah, what if, okay, so what if x was 2 and y was -2, right? If these two, if x is 2 and y is -2, then would you agree that this is true? 2 squared is equal to -2 squared. Is that true? 2 times 2 is equal to -2 times -2. That would be true, right? Yeah. So if I tell you that some number squared equals the other number squared, does that mean the two numbers had to be the same? Well, they weren't, were they? See, this is not true in general. This is not true in general. What we're saying here, though, is that if your bottom is a number, right, a, and these two powers, right, you have raised to some powers here, that if this is equal, then I guarantee you those two powers had to be equal every time. So this is a property we need it. And now we go try and solve these equations. So here, I'm going to take this first one. Oh, what's going on with this program? Every time I open it, I have to widen the page. All right, so here we go. If 4 raised to the -2x equals 1/64, they want us to find out what x is. So we're trying to solve an equation here, right? I'm trying to solve for x. What is x? What you should notice, though, is that x is up in the exponent, right? Anytime we've solved for x in the past, x has always been on the bottom. Here, x is on top. And that's weird because we've never really had that. So right now, we don't have a way of getting x from the top and bringing it down. We will later, just not yet. So the only thing we can do at this point in this class is to hope that the other side of the equation can be rewritten with something like 4 as the base. But you should recognize 64 as being what? 4 to the 3rd power. Do you all agree that's true? Now, do you agree with this? 4 to the -2x must then equal 4 to the -3. What did I do here? I brought it up, right? That's just a property of exponents. I brought it up as a negative power. And now do you see that you have the same base? 4, 4, and they're raised to 2 different powers, this and this. So what does that property tell us must be true? That implies that -2x must equal -3. And if you divide both sides by -2, you get 3/2, 3/2. Negative divided by negative is positive. So x equals 3/2 is the solution to this. Let's just check our answer, see if it makes any sense. If we take the left side of the equation, 4 raised to the -2 and then times x, right? Let's take our answer, it was 3/2. All right, so I'm just taking the left side and I'm plugging in 3/2 right there for x. What would happen here is these 2's would cancel. We get 4 to the -3, right? But that is just 1/4 cubed. And that's 1/64, which checks with what it's supposed to be. See? So if I recap this, we started with an equation. What we did was we tried to look at both of these and we said, oh, 64 is a power of 4. Rewrote it, property of exponents, set the two exponents equal to each other, solve the equation. Let's do another one. They get harder. Three raised to the 1 minus x equals 9 raised to the 2x. Any instinct as to what to do here? Because 3 and 9 are not the same base.
We automatically just change it to 3.
You can change it to 3. Yeah, sure. How would you change? You would change the 9 to 3, right? Okay, how? 9 is 3 squared, right? Okay, good. So let's rewrite this as 3 to the 1 minus x equals, now be real careful here. This has to become 3 squared to the 2x, right? That's what 9 to the 2x is. Now, going back to the properties from the very beginning of class, when you have something to a power, you multiply the powers, right? So if I have something to a power, I can multiply these two together, can't I? And that would be 3 to the 4x, right? 4x. 2 times 2x is 4x. So we get 3 to the 1 minus x equals 3 to the 4x. And now you see that you have the same base. And now you can take the exponents and set them equal to one another. 1 minus x equals 4x. And this is just a little linear equation, isn't it? Just move things around. You know, I'll just add x to both sides. I'll divide both sides by 5 and I'll be happy. X is 1/5. You can check your answer, but I'm not going to. I just wanted to show you in the previous example that you could check it by just plugging it in, right? Questions on that one? So the key there was to rewrite the 9 as a 3 squared. That was the key to the problem there. You like these? I can tell. I can tell you like this. Okay, let's try and, well, be careful. Be careful what you wish for, right? Actually, these don't get, they can get a little messy, but they aren't too bad. Okay, what about this one? 9 to the 2x times 27 to the x squared equals 3 to the negative 1. How do you mean factor of 3? Oh, make them all have 3s. Is that what you mean? Like rewrite the 9 with the 3 and rewrite the 27 with the 3. Yes. Yes, you can do that. You can't you said factor out of 3. You can't pull 3s out of these because of properties of exponents. You have to do this before you can do anything with the 9 or 27. But you could rewrite, you go ahead and tell me, you could rewrite this as what? 3 squared to the 2x times, now how can you rewrite 27? 3 cubed, right? And then times x, or raised to the x squared, and then that equals, well, 3 to the negative 1, let's just leave that alone, right? Now just use that property again where you have something to a power to a power. So this becomes 3 to the what? 3 to the 4x times 3 to the 3x squared equals 3 to the negative 1. Is that all right? Now you have 3 to a power times 3 to a power, right? Go back when you have same bases being multiplied, different exponents, you add the exponents, right? So I'm about to do that. I have same bases, different exponents, I'm multiplying, so I add the 2 exponents. So this should become 3 to what power? But careful, you're adding them. One of them is x, the other one's not, the other one's x squared. These aren't like terms. Yeah, 3x squared plus 4x. You can't do anything more with that, right? Because, yeah, one's x squared and the other one's x. And that must equal the other side, which is 3 to the negative 1. Now you finally have it where they have the same base, right? Different powers. So now I can set those equal to one another. And if I do that, what would I get? 3x squared plus 4x equals what? Negative 1, and that's a quadratic. We should be able to solve that, right? Let's see, I can move the 1 over. And now that will factor. 3x, x, 1, 1 plus equals 0. So if you had trouble factoring that, then you could use quadratic formula, but that's semi-easy factoring, I guess, semi-easy. When they tell you you need to know how to do factoring of trinomials, like they're not kidding, right? I mean, like it just never goes away. It never goes away. So this is it. We set each of these equal to 0. And then I'm running out of room here. X is equal to -1/3. And X is equal to -1. Understand? We have two solutions here.
So do we plug in both? solutions?
You could check them both. You could check them both. Yep.
What are we looking for?
Just that it's true. Like, look, let's try -1. Let's test our -1. I'm gonna plug it in here. So if I do 9 raised to the 2 times -1 times 27 raised to the -1 squared, does that equal 3 to the -1? All right, so let's see. This is 9 to the -2, understand? Times 27 to the, let's see, what's -1 squared? 1, so that's just 27. Does that equal 3 to the -1? Isn't that 1/3? That's what 3 to the -1 means, 1/3. And now this right here, could I drop that 9 down as a 9 squared? So 27 over 9 squared on the bottom, 81. Does that equal 1/3? Well, 27 goes into both of these, right? 27 goes into here once, 27 goes into here 3 times. So that reduces to be 1/3. Check, that works. That makes sense? Like that's how you would check each one, yeah. The other one would be a little harder because it's a fraction, but it should check out.
Both of them be an option, or is it just one or another?
No, yeah. So is it possible that you get an extraneous solution? We never squared both sides of anything, so we should be good with both solutions.
Okay.
Yeah. But both, yeah, it's not just one. All right, I think we have one more of these. So I wanted to just give you a minute to see if you might be able to figure this out on your own. I haven't necessarily shown you one of these, but take a minute to see if you can figure out. This is the last problem we have for the day. We're not going to finish right now. I know you're excited to go, but just see if you can figure that out. If 5 to the -x equals 3, what does 5 to the 3x equal? Take a minute. Anybody feel like they got it? Huh? You got 9? Okay. I did it earlier. I don't remember what the answer is, but I'll ask you how you did it in a minute. Anybody have a question? Anyone at home? Y'all got anything? Did you do 9 just by visual inspection, or did you actually do some sort of algebra?
Well, I think when I did it, it was 15. Because of that, I think the number over the base, so like 1/5, for example.
Uh-huh.
And I think I thought that it'd be 3 to 15 divided by 5.
So are you just plugged in a number? Is that what you're saying?
Yeah, because well, I was trying to figure out how it gets. So I think that
Yeah.
I was guessing that probably the device.
Oh, I see. Okay, I see what you're saying. You try to put 15 there to make the 3, like 15 divided by 3 will give you 5 on the right. I got you. Understand. Okay. Anybody else? Huh?
That's the kind of way I was thinking
Yeah.
about it. Trying to make them equal out.
You're trying to get them both to have the same base of 5, right? Okay. So my hint to y'all is that this is very different than what we just did, right? So watch what I do, and then once you see it, you're like, oh yeah, okay, that's not bad at all. Okay, it's just that it looks different. It's a different sort of problem. So watch what I do. I'm going to start with the left side. Okay. The left side. Do y'all agree the left side is the same as this? 1/5 to the x equals 3. Yes.
Then it has to be flipped. 5/1 to equal the full 5.
Does it have to be equal? I'm using the property like if we have x to the -2, that's 1/x squared.
Okay.
Or if we have 4 to the -1, this is same as 1/4,
Okay.
right? So if I have anything to a negative power, I can drop it down 1 over it. Is that okay?
Yeah.
So now what I'm going to do is I'm going to multiply both sides by 5 to the x. I'm clearing the fraction. Okay. When I do that on the left side, I get what? 1. Okay. Equals 3 times 5 to the x. Now, you cannot multiply 3 times 5 because of that order of operations. That 5 is trapped with the x. But I can divide by 3. So I'm going to divide both sides by 3. And what I get is 5 to the x equals 1/3. Now, what is it that I wanted to know? What's 5 to the 3x, right? Anyone know what I'm about to do? I'm going to cube both sides of the equation. Why? Let's see what happens. If I cube this side and cube this side, what's 5 to a power to a power? What do you do to these powers? Multiply them. What's x times 3? 3. That's why we did that. Okay. So this becomes 5 to the 3x equals, well, what's 1/3 cubed? You just cube the 1 and cube the 3, right? Cube each one. So you get 1/27. 1/27. Do you see there? We never solved for x. We never figured out what x was going to be, ever. All we did was manipulated the original expression into what we were trying to figure out. Yes. You could have done that also, just do a -3 power on both sides. I think that would have been a little, well, I mean, if you see it, you see it, right? You could have started out with the original problem and just done -3, -3. Right there. The negative times negative would be positive. You get 5 to the 3x here. And then this would be the same as 1/3 cubed using the property of exponents. Right? The negatives would drop down, and then that's just 1/27. That'd work too. That's clean. Isn't that clean? So either way. All right, so I have another problem I want to throw up here for you. That should be enough, though. What we've done today, that should be enough to get you through your homework, okay? Your homework problems, if we look at them now, the first section, there's a bunch of graphs, and then there's a bunch of functions, and you're supposed to match the function to the graph. So you can look at this one and be like, oh, this is, the negative in front of this reflects it over the x-axis. This is like a 1 being added to the back, so it moves it up 1. You can kind of match things up. And then the next ones are use transformations to graph these. So that's what we did earlier. We only did this with e to the x, but you can do this to any of these functions, like 4 to the x minus 1 plus 2. You know 4 to the x looks like growth. The minus 1 moves it to the right 1. The plus 2 moves it up 2. And then these solving, that's what we're doing right now. Okay, there's a bunch of them here. All right, so as much as we've done in terms of the solving, we're very, very, very limited on what we can do solving. Let me show you what I mean. Let's say I gave you this. 5 to the x equals 3 to the 2x plus 1. Find x. So here's the problem. We can't turn the 5 into a 3. There's no easy way to turn the 5 into a 3. On the previous problems, when we were doing like the one we had like the 3 and the 9 and the 27, those were all powers of 3, so it was easy. Here, there's no way. We can't do it. But there is a solution to this. There is a solution. I don't know the solution offhand, but what I could do is I could graph both of those. If I graph both those as functions, the first one, what was it, 5 to the x equals, what was it, 3 to the, was it 2x plus 1? What was it? Hold on. Oh, 2x plus 1, it's all right. 2x plus 1. So what we're actually trying to do is find the x where these two graphs hit each other. I did type that in wrong. Does it? See, it automatically does that. Shit. I have to put the plus 1 out front. There we go. So I'm trying to figure out where these graphs hit each other. I think it's right here. Right there. That's where they hit each other. The solution is negative 1.8691. That's the solution. How in the world would we find that? Okay. And right now, there's nothing we have, okay? There's nothing we have that can do this. Nothing, okay? Because again, we can't turn the 5 into a 3. We can't turn the 3 into a 5. So we're very limited in what we can do at this point. So the way we're going to eventually attack this is we're going to need to start working with the inverse function of the exponential functions. So we spent an entire class before we got to exponentials talking about functions and their inverses, right? If you have a function, is there a function that can undo it? Well, when you go back and look at exponential functions, right? The general look of every exponential function, are these functions one-to-one? Do they pass the vertical and horizontal line tests? Yes, right? They do, which means all exponential functions have inverses. And those inverse functions are what's next now. We need to talk about what's the inverse of these. And that, believe it or not, will allow us to solve any exponential equation. But right now, our hands are tied. We can only do specific ones very specially made for us. But after next section, we should be able to solve any equation that has x's up in the exponents like that. But it will require, we talk about their inverses, which are called the what functions? These are called exponential functions. What are their inverses called? Logarithmic functions. So if you've ever, I'm sure you've heard of logarithmic functions or logarithms. Logarithmic functions are just the inverses of these. All right, so that's what next class will be about. We'll look at all the wonderful properties, and then we can put it all together and solve equations. All right, I'm out of time. Y'all good? You understand what the homework is? All right, everyone have a great day.
Thank you.
All right, have a good one.